In this lesson, we'll talk about sum, difference, and cofunction identities. So here's a list of cofunction identities. The name refers to the fact that a trig function of a complementary angle equals to the value of the cofunction of the original angle. This property comes directly from the definition of trig functions. If we look at this right angle triangle, and the original angle is called theta, that the complementary angle is the other acute angle, which is 90 minus theta. And as we noticed before, for example, cosine of theta is a over c, but a over c can be considered to be sine of 90 minus theta. So we have this first identity, and the other cofunctions will have exactly the same property. Tangent of 90 minus theta is the same as cotangent of theta. You can always check this on the right angle triangle. So tangent of this angle is a over b, but a over b is the same as cotangent of theta. And you're welcome to check the rest of the identities. So to memorize this, think about cofunctions of complementary angles are equal. Now we are going to develop formulas for the first three trig functions, sine, cosine, and tangent, of sum or difference of angles. In a unit circle, if, for example, this angle is alpha and that angle is called beta, then the difference between alpha and beta is this angle. We also know the coordinates of each point on the unit circle. It takes cosine of the angle defined by the point and sine of this angle, cosine, sine. So, for example, this point is cosine beta, sine beta, because the defining angle is beta, and that point is cosine alpha, sine alpha, because the defining angle is alpha. Notice that if we rotate this triangle OAB backwards, so the terminal OB will actually be positioned on the x-axis. Therefore, instead of B, we'll have just a point 1, 0. Let's call it D. Then the other terminal A will be exactly at the angle alpha minus beta. So it will define a point C, which would have coordinates cosine of the angle, and the angle is alpha minus beta, and sine of this angle. So what we've done is just rotate this triangle to the new position, to that position here. And since rotation doesn't change the distance AB is the same as the distance CD. So by equating these two distances and working with the coordinates of those points as you see them, we can develop a formula for cosine alpha minus beta. And you're welcome to check this formula just by setting up the equation that compares these two distances. So distance CD will be this cosine alpha minus beta minus 1 in a bracket square plus sine alpha minus beta minus 0, that means just sine, square. That will be under square root, but on the other side of the equation you will also have square root, so the square root will cancel, and after some calculation and applying Pythagorean identity, you should end up with this formula. So I will leave this up to you to check this formula. Just in case if you have any trouble, this formula is developed in your textbook. Since in this lesson we'll develop a lot of formulas and they are maybe not so easy to memorize, I would suggest that you take a piece of paper and start collecting them because they will be needed for various exercises. So make a nice list of formulas so it will be easier for you to refer to. Okay, so cosine of the difference of two angles alpha and beta is cosine alpha cosine beta plus sine alpha sine beta. Now, if we replace beta by negative beta over here, then two negatives makes it positive, so we can produce a formula of cosine alpha plus beta. And that's the same cosine alpha. And remember, cosine of negative beta is the same as cosine beta, so the first part doesn't change. But the last part, instead of sine beta, we have sine negative beta, which means that we can pull the minus out of the sine, which will cause that this plus will change into minus. So this formula is direct consequence of the first formula just by replacing beta by negative beta. Okay, so if we have formulas for cosine of sum and difference, we can develop more formulas, for example, sine of sum of angles. Since cofunctions of complementary angles are equal, we can change sine into cosine, but then use complementary angle to alpha plus beta. However, complementary angle for alpha plus beta is 90 minus alpha plus beta. But that really means 90 minus alpha and minus beta. Now if you see this, we can treat the 90 minus alpha as one angle and beta as other angle, and follow the formula for difference of angles. So cosine of the first angle, cosine of the second, plus sine of the first, sine of the second. Okay, now we can use again the cofunction identities, which will tell us that cosine of 90 minus alpha is the same as sine of alpha. So that will be replaced by sine alpha. Then we have cosine beta. Then sine of 90 minus alpha is the same as cosine of alpha and sine of beta. So overall, we created a new formula. Sine of sum of angles is sine of first cosine of second plus cosine of first sine of second. So that's another formula for your list of formulas. And similarly as before, if we replace beta by negative beta in the previous formula here and there and there, then we create a formula for sine of difference of angles. Because cosine negative beta is the same as cosine beta, and sine negative beta is negative sine beta, so this sign will change. The rest will be the same. Okay, so now we have both formulas for sine and cosine. And using these formulas, we can create a formula for tangent of sum of angles. As we know, tangent is the same as sine over cosine, so let's write it down. Then we can use formulas that we already developed for sine of sum of angles, that's in the top, and cosine sum of angles from the previous slide, that's in the bottom. Now we're going to divide the numerator and denominator by cosine alpha, cosine beta, all terms by cosine alpha, cosine beta. This causes a lot of cancellations. Let's observe. Here we cancel cosine beta, so we end up with sine alpha over cosine alpha, which is really tangent alpha. Over there we cancel cosine alpha, so we have sine beta over cosine beta, which is really tangent beta. In the bottom we cancel cosine alpha, so we have cosine beta over cosine beta, which is actually 1. And finally, sine alpha over cosine alpha is tangent alpha, and sine beta over cosine beta is tangent beta. So we end up with this formula. Tangent of sum of angles is tangent of the first angle plus tangent of the second over 1 minus product of the tangents of the two angles. And as you may expect, the second formula comes by replacing beta by negative beta in the previous formula. So that will be tangent of alpha minus beta. The tangent alpha is just copied. Then tangent of negative beta, since tangent is odd, we pull the minus out and we end up with minus instead of plus in the numerator of tangent beta. Over 1, and then instead of minus we'll have plus because of the minus that we are taking from negative beta outside of tangent. So 1 plus the product of tangent alpha and tangent beta. So now you have all formulas about sum or difference that we're going to use. We don't have to worry too much about formulas of secant, cosecant, or cotangent of sum or difference of angles because the other functions are just reciprocals of the ones that we have. So it's enough to calculate those and take reciprocal, just in case if we need the values of the other three functions of sum or difference of angles. And here we have the first exercise. We need to find the exact value. Exact value means don't use calculator. We need to use special angles and possibly formulas for sum or difference of angles. So the exact value of sine of pi quarter minus pi thirds. Okay, so here in the top I listed our main formulas using the double sign. So the top sign goes with the top, the bottom goes with the bottom. So this way we can see all 6 formulas here. So we can use those formulas. For example, sine of difference of angles is here. Let's write it down. Sine of pi quarter minus pi thirds is the same as, according to the formula, sine of the first angle, sine of pi quarter, cosine of the second angle, pi thirds. Since we're talking about difference, we are taking the bottom sign, so minus cosine of the pi quarter and sine of pi thirds. Since each of those values we are able to recover from special triangles, then we should have no problem to give the exact answer. Sine of pi quarter, well, that comes from half of the square, 1 root 2, right? Because pi quarter is here. So it's 1 over root 2. Cosine pi thirds, oh, that comes from half of equilateral triangle, 1, 2 root 3. And pi thirds is this angle. So cosine is 1/2 minus cosine pi quarter, which is again 1 over root 2, times sine of pi thirds, which is root 3 over 2. Well, so we have already the answer, we just need to simplify it. This looks like it's 1 minus root 3, and in the bottom we have 2 root 2. Common denominator. Since we don't like to keep radicals in denominator, let's multiply the whole thing by root 2 here and there. And we end up with root 2 minus root 6 over 2 times 2, which is 4. So that's our exact answer for this problem. Notice that sine of pi quarter minus pi third is actually the same as sine of common denominator 12ths, so that will be 3 minus 4 pi, so it's negative pi 12ths. Okay, so this value is the value of sine of negative pi 12ths, or in other words, negative sine of pi 12ths. Well, as you see, the technique of taking trig functions of sum or difference of angles allows us to find out values for some other angles than the ones from special triangles. So we can find out exact values for more angles. The next problem asks us to find the exact value of tangent 75. 75 is not a special angle that we know, but maybe we can obtain this angle by using sum or difference of angles that we do know. We can change tangent 75 into tangent of 45 plus 30. And this way we'll be using special angles, so we'll be able to give the exact answers just after we apply the formula for tangent of sum of angles. So follow that formula. It's tangent 45 plus tangent 30 over 1 minus tangent 45 times tangent 30. Okay, tangent 45, as we know, it's equal to 1. It comes from special triangle, half of the square, 1 root 2. So tangent 45, yes, it's 1. Plus tangent 30, half of equilateral triangle, 1, 2 root 3. 30 is here. Tangent is 1 over root 3. 1 over root 3. Over 1 minus, again, tangent 45 is 1, and then is 1 over root 3. Okay, so we already have the exact value. We just need to simplify it. We can do it, for example, by multiplying the top and the bottom by root 3. That will give us root 3 plus 1 over root 3 minus 1. And again, it's a good habit to get rid of irrationality from denominator. So let's multiply the top and the bottom by a conjugate, root 3 plus 1, here and there. So in the bottom we'll end up with 3 minus 1, which is 2. And in the top we have perfect square of root 3 plus 1. So it's 3, square of the first, plus double the product is 2 root 3 plus 1. So we have 4 plus 2 root 3. So from that we can pull the 2 out, and inside will be 2 plus root 3. And now we're ready to reduce the 2. Final answer, 2 plus root 3. Exact value of tangent 75. Well, see if you can do the next exercise by yourself. Let's check. Cosine 15. How else can I rewrite 15 degrees? Well, it could be 45 minus 30. So we can use 45 degrees minus 30 degrees. And then follow the cosine of difference of two angles. So the bottom sine. Okay, that's cosine of the first angle, cosine of the second angle, plus sine of the first angle, sine of the second angle. So we have the following values. Cosine of 45 is 1 over root 2, but let's write it root 2 over 2 already, the rational version of it. Cosine 30, so it's this angle, it's root 3 over 2. Sine 45, the same as cosine 45, is root 2 over 2. And sine 30, 1 over 2. So overall, we have denominator 4. And then we have root 6 plus root 2. So that's our final exact answer for cosine 15 degrees. Now let's evaluate the following expressions. We have sine of an angle, cosine of different angle, cosine of the first angle, sine of the second angle. Well, that reminds me of a formula. Which formula will this be? Let's see. It must be a combination of sine and cosine, and we must have a sine plus between the two terms. So it's a sine of sum of angles. Therefore, as soon as we recognize this formula, we can write this is the same as sine of sum of these two angles, x fifth plus 4x fifth. Well, that's great, but we can actually add them. So that's sine of 5x fifth, which is the same as just sine x. So that was nice. We could simplify this expression really easy here. Let's see the second expression. Tangent 3x minus tangent 4x over 1 plus the product of these two tangents. So, it looks like the third formula here with the minus in the top and plus in the bottom, which means this is tangent of difference of angles. So that must be the same as tangent of 3x minus 4x. But this is the same as tangent of negative x. And since tangent is odd, we can pull the negative out. So the whole formula is really negative tangent x. Okay, the next exercise tells us that sine of certain angle alpha in the second quadrant has the value 24 over 25. Tangent of certain angle beta in the third quadrant has the value 3/4. And having this information, find out what's cosine of beta minus alpha. Well, first of all, let's apply our formula for cosine of difference of angles, which is over here. So cosine of the first angle, cosine of the second angle, plus sine of the first angle and sine of the second angle. Okay, let's see what we already know. The only thing that we know directly from the given information is sine alpha. This part is 24/25. Well, if we know sine alpha, we need to figure out what cosine alpha is. Let's draw a modeling triangle, right angle triangle. Let's say if this angle is alpha and sine of it is 24 over 25, then this side must be 24 and that one 25. Therefore, using Pythagorean equation, it's easy to find out the third side. That's actually part of Pythagorean triple. It will be 7. You may want to check on that just by taking square root of 25 square minus 24 square. That should give you 7. Okay, therefore cosine of this angle alpha must be 7 over 25 up to the sine. Well, what's the sign of cosine in the second quadrant? Cosine in the second quadrant is negative, so that will be negative 7 over 25. Good. Let's look at angle beta. Draw another modeling triangle. If this is beta, then tangent of beta is opposite over adjacent. So it's 3/4 like that. If this is 3 and 4 and this is right angle triangle, this must be 5, another Pythagorean triple. So what's sine of beta? Sine of beta is 3 over 5 up to the sine. And the angle beta is in the third quadrant. We know that sine in third quadrant, recall cast, sine in third quadrant is negative. So we have negative 3/5 instead of sine beta. And similarly, cosine beta is 4/5, and beta again is in third quadrant. Cosine is negative, so negative 4/5 over here. Good, let's put this together. That will be positive. The denominator is 125. Multiply numerator, it's 28. And then since this denominator is the same, we can write everything under one division bar. It will be minus 3 times 24, which turns out to be 72. So altogether we have negative 44 over 125. Final answer. Okay, let's try the same with sine alpha plus beta. You're welcome to stop the video and try these exercises on your own. And if you have any trouble, look at the video. Sine of sum of angles. We follow this formula with the top signs. So it's sine alpha cosine beta plus cosine alpha sine beta. And as before, sine alpha, we already know that's 24/25. Cosine beta, we figured out, is negative 4/5. Cosine alpha is negative 7/25. And sine beta is negative 3/5. So altogether we have, again, the denominator is 125. The first term is negative 4 times 24, which is negative 96. The last term, 2 negatives makes it positive, 3 times 7, 21. So overall we have negative 75 over 125, which could be reduced further by 25, leaving us with negative 3/5 as a final answer. And the last example, tangent of sum of angles. It comes from this formula, so it's tangent alpha plus tangent beta over 1 minus tangent alpha tangent beta equals. And let's plug it in values. Tangent alpha, we have those modeling triangles, we can refer to them. So tangent alpha is 24 over 7. And alpha is in second quadrant, so tangent in second quadrant is negative. Therefore, negative 24 over 7. Plus, tangent beta was originally given as 3/4, no problem here. Everything over 1 minus tangent alpha, which is negative, so we can actually write plus here. 24/7 times 3/4. And now the whole thing is to simplify this expression. Since this is a complex fraction, it's a good idea to multiply by a common denominator, the very top and the bottom. So let's multiply this by 28, which is 7 times 4. So 28 times the first fraction is like 4 times negative 24. So we end up with negative 96. 28 divided by 4 is 7 times 3 is plus 21 over 28 times 1 is 28 plus the denominator will be reduced, so it's 3 times 24, which is 72. And finally we have negative 75 over 100, which could be reduced by 25 to negative 3/4 as a final answer. Okay, the next exercise asks us to rewrite the expression in terms of trig functions of angle theta. So we don't want cosine of theta plus pi, we want just function of theta. Well, we could use the sum of angles formula again. So cosine of sum of angles is cosine of the first times cosine of the second angle minus sine of the first times sine of the second angle. But then cosine of pi, we know that's a quadrantal angle. What's cosine of pi? Well, it's negative 1. What's sine of pi? That's 0. Therefore, we end up with negative cosine theta. And the 0 times anything is 0. So that's the final answer. And we can actually see this fact on the graph of cosine. The cosine looks like this. That's pi. That's 2 pi. And that's pi half. Cosine of certain small angle plus pi. If this is my small angle, cosine is about this much. And if I add pi, I end up here. So the original value for cosine theta can be found over here, but with opposite sign. So if this angle is theta plus pi, I can claim that cosine of theta plus pi is the same as cosine of theta except with different sign. So it's negative cosine theta. And the second example, sine of theta minus odd multiple of pi. So for example, theta minus pi, theta minus 3 pi, theta plus pi, what would the value be? Well, let's follow the sign of difference of angles. Just to remind ourselves, we have the formulas here. So sine of difference of angles is sine of first, cosine of second. So let's write it down. Sine of the theta, cosine of 2k plus 1 pi as the input. So some odd multiple of pi. And then, since this is minus, we use the bottom sign. So it's minus cosine of theta, sine of this odd multiple of pi. Okay, let's analyze this. Sine of theta stays. Cosine of an odd multiple of pi. So for example, cosine of pi is negative 1. And then after adding any multiple of full periods of 2 pi, the resulting value of cosine will be the same, negative 1, because cosine has a period of 2 pi. So cosine of any odd multiple of pi will be negative 1. Now minus cosine theta, and sine of any odd multiple of pi, let's recall how sine looks like. Pi, and then any odd multiple of pi will result in 0 all the time. So that's times 0. So this part disappears, and we just end up with negative sine theta as a final answer. Again, we can see this on the diagram. Sine of any angle theta has, let's say, this value, and if we add pi to it, we'll land somewhere there. So the value of sine will be the same, but with opposite sign. So we can add 1 pi, or 3 pi's, or negative 1 pi. It will still be the same. Verify identities. Well, we develop formulas for sine, cosine, tangent of sum or difference of angles. Specifically, if those angles are exactly the same, we can create formulas for sine double angle, cosine double angle, tangent double angle, and those formulas are quite often used, so it's a good idea to memorize them, as well as add to the list of formulas. So those are special cases of our sum or difference formulas. Well, let's look at the justification, how come sine double theta is 2 sine cosine. Well, because sine double theta is the same as sine of theta plus theta. And then we can use the sign of sum of angles. So it's equals sine theta cosine theta plus cosine theta sine theta. Since both of these are the same, that's why we have 2 sine theta cosine theta. So from now on, remember that sine double angle is 2 sine cosine of single angles. Very useful formula. And now again, I will encourage you to try on your own. Justify that cosine double angle can be written as cosine square minus sine square of a single angle by using sum of angles formula for cosine. So cosine of theta plus theta can be seen according to this formula as cosine theta minus sine theta, which as you see is what we wanted. Cosine square theta minus sine square theta. Obviously, since we can replace either cosine square or sine square by using Pythagorean identity, then we can create equivalent formulas for cosine double angle. And for example, if I replace cosine square by 1 minus sine square, and then I have another sine square here, then the same formula can be written in the form 1 minus 2 sine square. So it's another version of this formula. Or even if I replace the sine square by 1 minus cosine square and then copy the rest, then I create a formula 2 cosine square minus 1. So that's the third version of cosine double angle formula. So cosine double angle can be memorized this way, or that way. I usually remember it in this form. That's the easiest for me. And then just in case, if needed, well, replace either cosine square or sine square by Pythagorean identity and create other versions of the same formula. And finally, tangent double angle. Again, tangent of theta plus theta. We follow this formula with the sum. So plus in the top, minus in the bottom. And we have tangent theta plus tangent theta over 1 minus tangent theta, which really is 2 tangent of angle theta over 1 minus tangent square. So yes, all these formulas are true. Try to memorize them, especially sine of double angle and cosine of double angle, at least one version, and also add those formulas to your favorite list of formulas. We have 2 more questions. Prove the identity. Well, we need to start with the left-hand side and show that it's equal to the right-hand side. So, left side, if I put these 2 fractions under common denominator, then I have sine theta cosine theta. In the numerator, I have cosine 4 theta times cosine theta, and then it's minus sine 4 theta times sine theta. Okay, so whatever I see in the numerator, it looks very similar to the first row of our formulas, right? If I assume that my alpha is 4 theta and beta is just 1 theta, then the numerator is actually the same as cosine of alpha plus beta. So that's the same as cosine of 4 theta plus 1 theta over sine theta cosine theta. Oh, that's great, because 4 theta plus theta is 5 theta. So yes, we really have right-hand side. We do have 5 theta here. And the last example, this may be a bit longer. We need to show that sine 3x is equal to this much. So let's start with the left-hand side and change your sine of 3x into sine of 2x plus another x equals, and then follow the rule for sine of sum of angles. So sine of the first, sine 2x, cosine of the second, cosine x, plus the same sine, cosine 2x, and sine 1x. So now we have sine of double angle, cosine of double angle to break down. Let's replace sine of double angle by 2 sine cosine. But then I multiply by another cosine, so it's actually cosine square. Plus cosine double angle, we can replace by the previously proven formula, cosine square minus sine square, and then times sine x. Notice that if I multiply sine x times this cosine square, then I will create a like term to the first one. So let's multiply through the bracket first. 2 sine x cosine square x plus sine x cosine square x and minus sine cube x. Oh, that's good. I already have 1 cubic sine. I need 3 more of cubic sines, but it's heading that way. Now let's put together the like terms. We really have 3 sine x cosine square x minus sine cube x. So now the fight will be to do something about this expression, to separate the sine and get rid of this cosine square somehow. So let's rewrite the cosine square in terms of 1 minus sine square from Pythagorean identity. Let's see what will happen. Now when I open the bracket, I have 3 sine x minus 3 sine cube. Oh, that's great. Minus another sine cube. So altogether I really have minus 4 sine cube. Wow, that's what I need to have. So this is the final formula for the right side. Okay, therefore the identity is proven.